Okay, so this is 16.7, change of coordinates. And I'm going to say slash mappings. All right, so the idea here is we have our usual xy. So let's start with just two variables. So our domain is just x and y. We'll talk about the space or three-dimensional version a bit later. Sometimes, for whatever reason, working in terms of x and y is going to be difficult. So what we're going to be doing in this section is creating a mapping UV from a different coordinate system, or one way to think of it is from a different coordinate system into x and y, so that we can work in terms of this different coordinate system, u and v, instead of x and y. All right. Another point of view is just a purely kind of functional or mapping point of view is this is a copy of R2, right, the plane. This is a different copy of R2, right? So we're going to create a function usually called a mapping, because function usually we think of as you have an input and the output is number, right? So here our inputs are points in the UV R2 copy of R2, the UV plane, and outputs are in the XY plane. All right. So the outputs are actually pairs of points. So for example, 1, 3 in the UV plane might go to 7, 2 in the XY plane. All right. Okay. So sometimes it's good to think of this as a change of coordinates, right? Instead of, thinking of your points in terms of x and y, you're thinking of them in terms of u and v. That's what we do when we talk about, for example, polar coordinates. That's exactly what this is, what polar coordinates is doing. Or sometimes it's really useful to think of it in terms of mapping. All right. The word mapping is really descriptive because this is actually what a map does, right? So you have in real life, let's say, is the XY plane. And let's say you have actually a physical map in your hand as the UV plane, right? So you have a physical map. This represents some location, right? And in the real world, the location is, of course, bigger. But every point here corresponds to one point in the real world. Every point here corresponds to a point in the real world. Okay. So mapping is a great description for this. And in the near future, we're going to be doing mappings not just from R2 to R2, but we're going to be doing mappings from R2 to R3. So maybe this map in your hand will describe locations on the globe, right? So in the real world on the globe, right? So that's literally what a map does for us. So here's the United States, South America, Canada, something like that, right? That is this down here in the real world. And every point here, right, we're right there, corresponds to a point on the globe. Okay. All right. So this is super, super important because it's really hard, for example, to work on the sphere because it's curved, but it's really easy to work on a flat copy of R2 because it's just R2, right? So essentially, what we're going to be doing in the near future is all the problems on the sphere that we need to solve, or all the problems regarding the globe in real life, we're going to convert it to a problem on just a regular R2, where again we can do very simple or comparatively simple math compared to if we had to work natively on the globe. All right, but that's for the future. Today is just going to be R2 to R2, but the idea is still the same, right? You can think of it as a paper map versus the real world in terms of the spirit behind what's going on. All right. So one issue we'll be seeing is that, so again, we're going to be doing from the UV plane to the XY plane. Our maps, at least in this section, are always going to be going from UV plane to the XY plane. So what's going to happen is grids here right, are going to go to differently shaped regions on the other side, right, in the image of this map, right? So this grid, for example, might go to something that looks like this on that side. Okay, so perhaps one of the applications, well, the application we'll be doing today is that regions here, which are kind of complicated, correspond to regions here that may be very simple. All right. And what we're going to be doing is integration. We'll be integrating, for example, maybe we want to integrate over a difficult looking region like this, right? A very curved region over here. But instead of working here, we're going to work on this left-hand side. All right. Where, for example, if we want to do integration on this left-hand side, you can see it's just going to be over this region is just going to be a double integral from a constant to a constant, right? And then a constant to a constant. Okay, because it's just a regular straight rectangle, right? Whereas on this side, on the right-hand side, if we wanted to integrate, we can see if I wanted to integrate, for example, with respect to dy first, I'm going to have to break it up into two integrals, right? This side versus that side is going to have to be a different integral. And then if I want, on the other hand, if I want to integrate with respect to x first, I'm going to have to integrate like this. And then there's going to be also a transition, down here where I have a separate integral. So the integral on the right-hand side, I'm going to have to do two integrals, okay? Versus the integral on the left-hand side, super easy, just constants, okay? This is literally what's happening when we integrate using polar coordinates. So in polar coordinates, we have, instead of u, let's call it r, and we have theta, right? So let me put this this is our u, and this is our theta. We're going to try to use u and v as much as possible today, just so we can get used to it. And what happens here in terms of x and y is, well, if r is a constant, right, looks like that on this side, right, in the uv or the r theta plane, these are r constant, that theta is moving, that goes to, well, r is constant, theta is moving here. All right. And then when theta is constant and r is moving, that goes to these guys here. All right. So you're kind of breaking up, or one way you can think of it is you're breaking up your region xy in the xy plane. Instead of using rectangles, you're using it different shapes, right? Up here, it was using, some curved rectangle looking like shape. Down here, it's you're breaking up your xy plane into kind of these sectors. Okay. But again, kind of working with sectors might be hard. So you work on the left-hand side instead, where that sector right there is actually corresponding to, just a flat, just a regular rectangle on the left-hand side. So that's why when you integrate kind of circular regions in terms of x and y, it might be unpleasant. But when you convert to polar coordinates, you're integrating over regions which are very simple. All right, we'll make this kind of correspondence much more formal when we actually talk about the actual conversions. Okay, in 3 dimensions, literally the same idea. We're going to focus mostly on 2 dimensions just because it's easier to kind of get a grasp of, and it's easier to draw pictures. But we can do literally the same thing in 3 dimensions. And polar coordinates we saw can be thought of as transformation in this way, right? Cylindrical and spherical coordinates, same idea, okay? Except in space, right? So you have 2 copies of space. Maybe here you would call it u, v, and w, x, y, and z, right? Every point here corresponds to a point there. And again, maybe the region in the xy, in terms of integration, maybe the region in the xyz plane is too unpleasant, too curvy, and hard to work with. So you create a new coordinate system, or you create a mapping so that that curvy region on this side looks like a nice rectangular box, for example. All right. And that's, again, literally what you do when you work with spherical and cylindrical coordinates frequently. All right, but we'll get to that after we talk about one variable calculus. So the idea here is that we're interested, at least for now, we're interested in this whole thing, this whole idea of mappings or coordinate transformations in the context of integration. We want to be able to integrate kind of easier, right? We want to transform hard integration problems into easier integration problems. Like I said, that's what we're focused on today. In the future, we'll be using these mappings for very important other things. But that's our focus for today. So one variable calculus, we've actually done literally the same thing in the past when we had, let's say, x and y. We had a function we wanted to integrate, let's say from here to here. Let me get rid of this guy here. So a to b, right? We wanted to integrate this, and perhaps the integral was too hard, right? So what we do is we do substitution. And from our kind of point of view for today, we think of substitution not as kind of just transforming one variable into another. We can think of substitution as a mapping from one copy of R, one copy of the line, to another copy of the line. All right? And what we hope is when we kind of port the problem from variables x into the variable R, things will become a lot easier. All right? And that's literally what substitution does for us. Okay, so how do we actually do this? Well, the idea is if we want to integrate, so again, let me say this is f of x, we want to do a, b, f of x dx, right? So one way to think of this is we take, if we have this kind of transformation or this mapping, let's say this guy goes to a and this guy goes to b, all right? And let's chop this guy up into equal spaced segments. When we push these equal spaced segments to the right-hand side, right? In other words, when we apply our mapping, they're not going to be equal spaced segments anymore necessarily, right? Just like up here, when we push this nice rectangle there, it's going to turn into something that's curvy. All right. So down here, it's the same idea. Equal space things are not necessarily going to be equal space. So maybe this one is kind of close together, but maybe one of them is very far, something like that, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Let me add one more. Okay. All right. So how do we actually kind of do the integral on the right-hand side that's in terms of x? How do we do it in terms of u and still, of course, get the same answer? That's what we're looking for, right? Well, one idea, one approach is to look at, so how do we integrate? We integrate by adding up rectangles, right? In one variable calculus. So areas of rectangles. So what we can do is we can take each of these guys here, right? And we can look at, let's say, the value of my function above this point here. So I take this point here, that maps to a. The height at a is that value. So I'm going to keep the same value on this side. Okay. The next guy, I'm going to take the height right there. Whatever height that is. If that's height 3, then I'm going to have height 3 on this side. Okay. Where this guy corresponds to the second hash mark. All right. The third hash mark right there. So here I do that. Same height. Okay. Let me actually try to make it the same height in this picture. Same height. Something like that. Okay. And we keep doing this. There, there, and there, right? Perhaps we get a picture like there, there, oops, sorry. There and there. I guess in there. Okay. And what we do on this left-hand side is we can add up these rectangles, right? Add up the areas of the rectangles. Add this up, plus that, the areas, plus that, plus that, plus that, plus that. Okay, so this is kind of a first try at calculating the area under the curve on the right-hand side of the picture using the left-hand side of the picture. All right, because again, maybe the right-hand side of the picture is just too hard. All right. Okay, so again, the nice feature on this left-hand side is that each of these guys here, each of these hash marks are equally spaced. Okay. However, if we do this, if we try to integrate this way, so if we add up all these areas of these rectangular regions, we're not going to get the right answer. If we add them all up, we're not going to get this integral right here. We're not going to get the area under the curve. Why? Well, because things are equally spaced here, but they're not equally spaced on the right-hand side. All right. So for example, this rectangle right there, right, looks like this, right, with a very thin base. On the other hand, let's say it corresponds to this fat rectangle over here, right? So when I calculate this area here versus that fat area here, it's not going to be the same number, right? This one has a bigger base. They both have the same height by the way I kind of ported the function backwards, right? Where again, this value is the same as that value. This value is the same as that value. This value is the same as that value, and so on. Okay, so when I ported the function back and I add the areas, this area here is not exactly the same as that area there. And so I cannot just do essentially what I'm kind of wanting to do is essentially integrate something like this just from the one endpoint to the other at just du, right? It doesn't work because this guy is too fat compared to that guy is too thin, all right? Okay, so what I need is I need a factor right here that accounts for the different width of these rectangles in a way, all right? And if you're thinking of substitution from one variable calculus, right, then you know where this is going. That factor is actually the factor that comes in when you do substitution, right? So that factor, the dx du essentially, needs to be there because the rectangle here is different size from the rectangle there, all right? All right, so if we do want to match these rectangle sizes, how actually do we do this? Well, let me, again, we're kind of thinking of this in terms of rectangles. Let me call this, the width of this rectangle on this side, delta u, all right? And again, all of this in terms of the actual mathematics, you do this as sums, and then you let delta u, for example, go to 0, and then you work the limit, and then that ensures everything is actually accurate as to, for example, area under the graph, all right? Okay, but we just need enough to kind of understand the basic idea. Okay, so let's say the width of each of these guys on this left-hand side is delta u, all right? So the question is, if this is delta u on this side, what is this width on the right-hand side that it corresponds to, right? Like I said in this picture, it looks like it's wider, right? But of course, it could also be thinner, right? So maybe maybe this guy here, it has width delta u as well, right? Because we're doing evenly spaced on the left-hand side. But this side here on the right-hand side of the picture is too thin. It's thinner than delta u, right? So on the left-hand side, we would be adding, in a way, too much area compared to what we actually should be adding. Okay, so how do we get this factor which kind of corrects for this? Well, one way you can reason this out is if I go from this point here to that point there, right? I've moved a distance of delta u, right? Okay, so if this first point, this left-hand point, goes to there in the fat rectangle, and this second point goes to that point in the fat rectangle, what is that new distance, right? That's essentially my question, right? That should be the correcting factor right there, right? That corrects for the width of the rectangle on the right-hand side. So what should that be? Well, a good way to think of this is if I move delta u here, how much should I move there, right? So now let me give a name to this mapping. I'm going to call this mapping x of u, all right? Okay, so u's are my inputs, and in a way my outputs are locations on the x-axis. So that's why I'm calling it x of u, all right? And we're going to be following the same pattern for multivariables. All right, so it is a little weird, right? We're thinking on the right-hand side of x as a variable. U is a variable. However, our mapping name is x of u, where here we're thinking of x as the name of a function. Okay, so you definitely want to kind of get used to that. Okay, so if I call this function x of u, well, if I move delta u in the domain, how much should I move in the range? Well, that's exactly what the derivative tells us. It should be we're in one variable, so dx du delta u, right? Approximately, of course. All right. So the width of that fat rectangle there is roughly dx du times delta u, right? That's literally what the dx du means, right? It's rate of change. So if I move, remember a one variable calculus, if I move this amount, right, from here to here in the x direction, how much does my y direction change? That amount, right? That's determined by the derivative, right? It's the rise over the run in a way, the slope, right? If I move this much here, how much do I move up? That's determined by the derivative. If I move one step here, I should move df dx steps upwards to stay on the graph of my function. Okay, so the width of this rectangle here should be dx du delta u. All right, so if I account for this by sticking that in right there, right, in terms of my my integral on the left-hand side, f, and then dx du, right? Then if I do this integral here, the answer that I'm going to get is actually going to match the area that I want, the area under the curve on the right-hand side. Okay. All right. And that's literally exactly what you do when you do substitution, right? That term right there, when you do, for example, u equals x squared, and you do substitution, du equals 2x dx, right? Then that means your dx equals 1 over 2x du. And what happens is you stick that 1 over 2x right there, right? That 1 over 2x is dx du, right? Because du dx is 2x, right? Because u is equal to x squared, right? And so the inverse of this is going to be that guy right there. Okay, so in one variable calculus substitution, we're doing things a little backwards from what we're going to be doing today. So in one variable calculus substitution, we usually write u equals x squared, right? So in a way, you can think of that as u as a function of x, right? If I give you an input of x equals 1, then the output is u equals 1. If I give you an input of x equals 2, the output is u equals 4, right? So I'm kind of describing things backwards. So for this u equals x squared, in today's language, I would be saying instead x equals square root u. All right. Okay. The way we did it in one variable calculus was nice because it was very straightforward because it was one variable calculus. Things were kind of relatively simple. But kind of doing it the way we're doing it today, where we think of kind of the inverse map compared to one variable calculus, is going to be better for the multivariable setting. All right. Okay, so again, if you were doing in one variable calculus a substitution, u equals x squared, that's equivalent to today doing the mapping from the u line to the x line, the mapping x equals square root u. Or let me even write it kind of more formally to emphasize that we're thinking of x as a function of u. So x of u is equal to square root u. Okay. All right, so that factor right there is the correcting factor to make sure our areas are being calculated correctly, right? Because ultimately, again, we don't really care about areas under the graph on the left-hand side. We care about the areas under the graph on the right-hand side, right? So we do need to have this corrective factor. All right, so that's the idea behind what's going on. What about the two variable situation, right? So two variable situation, uv, we're going to xy, right, under a mapping. And again, this mapping, I'm gonna, in the same way as we did it just now with one variable, the mapping is gonna be x of uv, y of uv. All right, and we'll often write it just like this, all right? Okay, and again, you think of this as, right, every point, if you give me a point in the UV plane, let's say 1, 3, right, let me do it like this, 1, 3, U equals 1, V equals 3, where is that going to go to in the, what point does that correspond to in the XY plane? Well, it corresponds to X of 1, 3, Y of 1, 3. All right. So it goes to that point right there. All right. Whatever this formula is, whatever that formula is. Okay. All right. We'll be writing down some examples of formulas and stuff in just a couple of seconds. But in terms of the picture, the idea is, again, we've actually drawn the picture already, right? Let's say, sorry, let me draw the XY plane. Let's say we want to integrate over this terrible looking region, right? Again, we don't really like it because if I integrate with respect to dx, I'm going to have to split it into two integrals, right? With that as our dividing line. If I integrate with respect to dy first, I'm going to have to split it into two integrals with that as our dividing line. So it's kind of unpleasant, right? So I don't want to integrate with respect to x and y. So I create this mapping, right, where I go from uv to the xy plane and where, let's say, a rectangle goes to that guy right there. Okay, so then the integral on the left-hand side is just going to be, right, let's say this is 0 to 2, let's say this is 0 to 4, right? My integral is just going to be 0 to, let me write, u equals 0 to u equals 4, v equals 0 to v equals, u equals 2, v equals 0 to v equals 4, du dv. All right. Okay, and of course, whatever function, we convert that from, naturally the function would be in terms of x and y on the right-hand side, but we would have to convert that to u and v when we do the actual integral, right? But the important thing is, right, this guy here is kind of curved. The areas kind of don't match, just like in the one variable calculus example. And so you need a correcting factor right there. All right, so what is that correcting factor? That's what we're going to talk about right now. Okay, so again, the whole point of this is that this should be equal to f dy dx, right, over our region. Okay, so what is that correcting factor? Well, if you did the extra credit from the last homework assignment, then you kind of know, because that's exactly what it was. What happens is, let's draw the two xy, uv again. So what happens is if I take this into if I break this into a grid, right, which is what we do when we actually integrate, I'm going to end up with some sort of grid-like thing on the right-hand side, right, curved and ugly. However, if I take these grids on the left-hand side, take them really, really, really tiny, right? For example, this guy here maybe delta u, this guy here delta v, right? Very tiny numbers. Then essentially, this rectangle here is going to go to something very much like a parallelogram on this side. All right. The technical discussion here would be the mapping from here to here can be approximated by tangent plane approximation or linear approximation. And if you did the linear approximation, then the mapping would just be a simple linear mapping where rectangles go to parallelograms. All right. So the correction factor is going to be the area of this parallelogram versus the area of this rectangle. All right. Okay, so what is that? Well, if you think about this, just basically in analogy to what we did just now with the one variable situation, this vector right there is going to be roughly described by d I guess I should say something just to be more precise. Let's say this straight horizontal line segment goes to that guy right there, all right? And this vertical line segment goes to this vertical line segment there goes to that, all right? Okay, so in a way, this horizontal, the u corresponds to that direction there. Okay, so if you think about this in terms of linear approximation, you do some calculations, which essentially is exactly what we did just now with substitution, a one variable calculus substitution. And if you did it in the extra credit, you will have literally done that. then you'll see that this guy here, this vector right there, is going to be d, so I'm calling this x of uv, comma y of uv, right? So I'm thinking of x and y as the name of my functions. So I can say dx du, comma dy du as a vector, all right? And then this guy right there is going to be dx dv, comma dy dv. Okay. And then times your deltas, all right? But delta u, delta v, right? So I guess I should write that down. Delta u, delta v, right? So the length of this guy right here is the length of this guy right there, and the length of this is the length of that, roughly, all right? Or that's the spirit behind what's going on, okay? All right, so the area on this left-hand side is delta u, delta v, right, of this rectangle here. But the area of this parallelogram, if you think about it, it's actually going to be the determinant of dx du, dy du, dx dv, dy dv. All right. So this guy right here essentially forms the area of that parallelogram. And then times delta u, delta v. Let me stick that in. Delta u, delta v. All right. So you may have guessed, right? We're going to be changing the delta u, delta v's to du, dv as we take the limit as the delta u's and delta v's go to 0. So the important thing is essentially this guy right there is our correction factor. Okay. All right, how do I know the determinant is the area of that parallelogram? Well, if you think back to, let's say, the cross product, right? Let's just extend the z direction outwards toward the out of the screen, right? Then we can think of these two vectors right here, dx du, dy du, and then dx dv, dy dv, dx du. We can think of them as vectors in space, where just the third coordinate is 0, right? If I take the cross product of that, dx dv, dy dv, comma 0, right? This is the cross product, which we haven't looked at in a long time, but here's where we kind of start to use it. If I take the length of that, remember this was the area of a parallelogram, right? That was one of the features. That was the kind of geometric interpretation of the length of the cross product, right? It was exactly the area of the parallelogram formed by the two vectors that you're crossing together, right? So literally, that's exactly what we want, the area of that parallelogram. Okay, and if you calculate this cross product, well, ijk, we're going to get dx du, dy du, 0, dx dv, du dv, that's dy dv. That looks like a u up here, dy dv, 0, right? What is the cross product? Well, because of these two zeros, it's going to be really simple. It's just going to be dx du, dy dv minus dx dv, dy du times k, right? But we only care about the length of the cross product. So the length of that, right, is just going to be this guy in here. Okay, and what is that? That's literally exactly the determinant up here. Okay, so the determinant of this matrix right there is our correction factor. All right. So this guy is called the Jacobian. Okay, and it's directly analogous to the dx du that we saw in one variable calculus. All right. Okay, so essentially what we're saying is if I want to integrate something on this side, dy dx, for example, right, f over some region R, I can convert that to an integral on this side over, the whole point of this is that over a simpler region on this side, same f, but of course after converting everything to u's and v's instead of x's and y's on that side. And then I have the correction factor, determinant of all that guy, this guy up here, dx du dy du, dx du dy du, dx dv dy dv, and then du dv. All right. So this is kind of this portion comes from kind of looking at the region of integration. This guy is looking at, of course, the function we're integrating. Okay. All right, a couple notes. You got to be a little bit careful when you do this kind of transformation or this kind of mapping. By the way, our book calls these transformations, but I think mapping is a much better word. It's a better word because in the future, we could be working with stuff where the word mapping makes kind of more intuitive sense than transformation. Okay, same thing though. All right, so things we have to be careful about. So remember in one variable calculus even, if you weren't careful about substitution, sometimes you could get in big trouble. So for example, if you do u equals x squared, right, and you had, for example, x equals minus 1 to 1, right, and you tried to convert that just completely naively into u's, right, you would say, well, when x is minus 1, u is equal to 1. And when x is equal to 1, u is equal to 1. So it looks like you're integrating from 1 to 1, which is always just going to be 0, right? So what was the problem there? The problem was that this guy right there, u equals x squared, is not a one-to-one mapping, right? So there's going to be multiple x's corresponding to the same u. Very bad. So in one variable calculus, how would you resolve this? Well, you would break this into two integrals. If you insisted on doing this substitution, you would have to break it up into two integrals like that, and then do the substitution of each of them individually, right? So here, same idea, right? So if your mapping is not one-to-one, if it's kind of, you have multiple points corresponding to the same point on either side, ultimately your integral is not going to be accurate. It's not going to be what it should be. Okay, so these mappings ideally should always be one-to-one. All right, so one thing on the left corresponds to one thing on the right exactly. All right. Okay, we'll see an exception to this situation in just a few minutes, which we kind of already know of. But usually well, let's say it like this. This is the ideal situation. All right. If it's not ideal, there are ways around it sometimes. Okay, let me look at an example of a mapping, and let's work out kind of what it looks like, just so we can see, first of all, a sample mapping, and second, we can see how to kind of figure out the regions that are kind of appearing in these kinds of mappings. So let's say I have UV, and I'm going to define a mapping to, again, UV to, we're going to stick with UV plane to XY plane for pretty much the whole day today. All right. Okay, so UV to XY. So again, we're thinking of this as a mapping from a plane to the plane. All right. Let me write down a definition of this mapping. So let's say U comma V. Let me write like this. So let me write down a couple of bits of kinds of notations that we can write this in. Sometimes we can give this mapping a name. Let me call it capital F. All right. Then I could write something like F of UV is equal to something. Right. It's going to be something comma something because we need an X coordinate and a Y coordinate. And then, whatever the formula for this mapping goes inside here, right? So for example, let's do a simple one, 3u plus 4v, and let's say u minus v, okay? So this is kind of a more function approach to looking at this thing, right? Everything is in terms of this kind of function capital F, right? And again, we're not calling it a function because the word mapping is a better word. Okay, alternatively, we can also describe it like this. This is a very common way to do it. UV goes to 3 plus 4V, U minus V. All right, so we usually use this kind of arrow to represent what one point goes to under a function or under a mapping. Okay. So this is another way to describe the same thing, right? And yet another way would be x of uv comma y of uv is equal to 3u plus 4v comma u minus v, right? Or we could just write them separately. X of uv equals 3u plus 4v. Y of uv is equal to u minus v. We often do this when we talk about, in the past, when we talked about parameterizations of curves, right? We've used the same notation, x of t equals something, y of t equals something, all right? Or if we're really lazy, we just go x equals 3u plus 4v, y equals u minus v, okay? Nice and compact, but the danger of this last one is that you're not kind of explicitly seeing things in terms of functions, right? In this second to last expression, we're literally seeing x is a function of u and v. So we're literally seeing that x depends on u and v. Whereas the second one, you don't see it as clearly. And so it often gets people confused, right? Because oftentimes we think of x as a variable and u and y as a variable, and also u and v as variables, and then now we have these variables equating to each other. Sometimes it can be confusing. So this kind of form above, we're explicitly kind of emphasizing that x is a function that depends on u and v, right? And same with the y. In any case, we'll be using all of these notations, all over the place. So you should definitely kind of get comfortable with seeing them all. All right, in any case, let's work with this particular mapping. So again, f of uv3 plus 4, okay. I'm going to rewrite it over here. Oh, it's actually right up there, but let me rewrite it anyways. 3 plus 4v, comma u minus v. So let's see so we've been talking about, how rectangles transform. So let's just see an example of how that happens in this particular example and how we would figure out, right? So if I have a rectangle here, what does it go to on this side, right? What shape does it go to on this side, on the right-hand side, okay? All right, so let's do this one in a very kind of simplistic and naive way, just a very brutal way, right? We're just gonna see, okay, this line right there represents points where u is moving, but v is constant, right? So v is equal to 0, okay? All right, well, what object does it go to on the right-hand side, right? In other words, if I plug in points here, 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 and so on, where do they end up on the right-hand side? That's what I'm asking, okay? Well, all these points that I've just marked, they're points where v equals 0. So where do they go on the right-hand side? Well, they go to f of u comma 0, right? Because v is 0. And so I just write that down on the right-hand side. This is, sorry, that's a 3u there. 3u plus 0, comma u minus 0, all right? So this object right here on this right-hand side is going to be the object that on the left-hand side corresponds to a horizontal line, all right? All right, so how do we actually figure out what this is? Well, it's the same idea as this is actually literally a parameterization, right? Because we're only at this point working in one dimensions because v is set to be constant, okay? And we're doing this so that it's really easy to see what's going on. All right, so what is this on the right-hand side? Well, a good way to kind of figure it out is this 3u is x, this u is y. So x is equal to 3u, y is equal to u. Putting that together, that tells me x is equal to 3y, which tells me we're more comfortable looking at it like this, y equals 1/3 x, right? And so what is that? That's a line of slope 1/3. So something like that, all right? Okay, so as I move along this line, horizontal line here, right, where v is 0, on the right-hand side, my outputs are going to be moving along this diagonal line over here on the right-hand side. Okay. All right, we can do exactly the same analysis. For example, I can do this vertical segment here, right? What is that? That's where u is 0. Okay. So where does that go to under this mapping? What's the output of this mapping? Or often it's called the image of the mapping. Well, that's going to be 0 comma v, right? And that's going to be 4v comma minus v. Okay. And if you do the exact same analysis, right, x is equal to 4v, y is equal to minus v, that tells me x is equal to minus 4y, which tells me y is equal to minus 1/4 x. And so what we get is the kind of line segment corresponding to a vertical line segment here, or the vertical line corresponds to something which is sloped minus 1/4. So maybe something like that on this side. Okay. Maybe I do a different color. So this is there, the vertical line goes to that guy there. Okay. All right, and you can do literally the same thing. This horizontal segment here is at a fixed height, right? So this is where v is constant. For simplicity, let's just say this is at height 1, right? What would that correspond to on the right-hand side? Well, you just take your formula again for f, you plug in v equals 1, and you're going to get, again, a line on the right-hand side. Okay, what is it going to be? It's going to turn out to be a line like that. All right, and if you do this line segment here, it's going to be a line like that. All right. So ultimately what happens is this parallelogram region here is corresponding to this rectangular region there. Okay. All right, and this is kind of what you expect if you've done some linear algebra, because this particular mapping that we have is a linear mapping, right? And so linear mappings take parallelogram regions to parallelogram regions, right? Where in this example, the rectangle is a special case of a parallelogram. Okay. All right. So, for example, where might we kind of use this? Well, if we wanted to integrate over this region on the right-hand side, and it's kind of unpleasant for us, maybe we want to do this change of coordinate idea to instead integrate on the left-hand side. All right. And again, the integral on the left-hand side, if we integrate in terms of u and v, the limits of integration are going to be really nice, right? Constant to a constant, and then for the inner integral, constant to a constant for the outer integral, right? So that's perhaps one application. At least that's the application that we kind of focus on today. All right. All right. Of course, in reality, if your function is more complicated, we'll see an example in just a few minutes, it's not going to be necessarily a rectangle going to a nice parallelogram like that, right? It could go to something horrible, horribly curved, all right? But this is a really good example because the computations are relatively simple, and you'll see some exercises involving exactly this kind of transformation. All right, so let me do a actual example of finding a mapping, right? So normally, so this was I gave you the mapping, and essentially I wanted you in this problem to figure out what this mapping looks like in a way, right? In quotes, right? So what it looks like is a rectangle like this goes to a parallelogram like that. Okay. But normally, at least in this section, what we're going to be doing is we're going to start with something on the right-hand side, and we want to find a mapping that corresponds to that region on the right-hand side. We want a mapping so that region, maybe it's really ugly, corresponds to a nice simple rectangle. All right. So normally we start with the right-hand side. Okay, and again, you'll see a lot of examples in the homework where the region on the right-hand side is a parallelogram. So let's do a parallelogram example. So let's say, so this is, again, we're starting out in the xy plane, and we want to discover a mapping so that this parallelogram right here goes to a nice simple rectangle on this side. All right, let me do a rectangle that ultimately ends up like this. Okay, uv. Right? And let me put some, we're going to actually do this. So let me put some coordinates here, 3, 1. Let me do this. I'm going to move this up a little bit. 10, minus 4. And let's put 5, 7 there. All right. That looks a little messy. Let me fix this. 10 comma minus 4. Let me make this a little shorter. That's an x. Okay, so here's the problem. For example, I have an integral. Let me call this region R. So I have an integral, dy dx, of some function, doesn't matter, and over the region R, right? I notice it's too hard to work with because the region is horrible. I'm going to have to break it up into two integrals or whatever. I don't feel like doing that. So I'm going to figure out instead a transformation that goes from uv to xy, where a rectangle, simple rectangle, goes to this horrible parallelogram. Okay, and then what I'm actually going to do is I'm going to do the integral. I'm going to actually execute or compute the integral on this side, du dv, and then here's the determinant, the Jacobian term. Right? But again, the advantage here is that that's a constant, that's a constant, that's a constant, that's a constant. Okay, so we hope that that'll be easier. All right, so how would I actually do this? Well, for this particular kind of example where we just have a nice simple parallelogram, I think a good way to do it is to figure out this vector right there and that vector right there. All right. I've arbitrarily chosen this point as kind of my base point. Ultimately, what I'm going to do is I'm going to make 0, 0 go to 3, 1. All right. I'm going to make this horizontal line segment here go to that that segment of the parallelogram, and I'm going to make this vertical line segment go to that part of the parallelogram. Okay. All right, we already know that parallelogram, these kinds of maps, I'm going to be doing a linear map because why work with something that's worse, right? Linear is great. And so already, immediately, I know that from linear algebra, if we've done linear algebra, I know that once I figured out just a couple of these parameters, I'm all set. All right. Okay, so let me actually write down some of these vectors here. So this guy right there is going to be what? Well, that vector is going to be 10 minus 3, 7, comma, minus 4, minus 1, so minus 5. All right. This vector over here is 5, 7, minus 3, 1. All right, so 2, comma 6. Okay, so what I ultimately want is, again, I want the horizontal segment to kind of correspond with this 7, comma minus 5, and a vertical segment to correspond with the 2, comma 6. Oops, wrong color, but let's leave it like this. Let's not. Okay, so what I want is essentially, or one way I can say it is I want 1, comma 0 to go to 7, comma minus 5. All right, so 1, comma 0 will be here. So what I'm setting up is this point is going to go to 3, comma 1. The second point is going to go to 10, comma minus 4. All right, and then this vertical point right there is going to go to 5, comma 7. Okay, and then so 0, 1 is going to go to 2, comma 6. All right. Okay, so how does that work? Well, from here, I wrote it in terms of vectors because if you know linear algebra, then you can actually just figure it out straight from here, right? Thinking of these think of this as a linear transformation in linear algebra. Okay, but alternatively, if you don't know linear algebra, you can just think of it like this. I want 1, comma 0, u, right? So that would represent points, horizontal points along the x-axis, right? To go to 7, comma minus 5, u, all right? And I want 0, comma 1, v, which is this vertical v-axis. I want it to go to, let me do these, 2, comma 6, v. All right. Okay, so putting these together, if you kind of think about it in this way, what I'm saying is u, comma 0 should go to 7u, comma minus 5u. All right, and 0, comma v should go to 2v, comma 6v. All right, and so ultimately u, comma v goes to just the sum of those two, right? Because if I add the left-hand sides, u plus v, u comma v. So if I add the right-hand sides, that's what I'm going to get as the right-hand side. Again, this all works because I'm creating a linear mapping. Okay. All right, so this will already, if I stop here, what I'm going to get is a mapping that takes rectangles to parallelograms of this shape up here. Okay, which is pretty much going to be decent enough, because what that means is with this mapping that I've already discovered, some rectangle up here is going to correspond to the one that I want. All right. Now, if I want to be, if I'm kind of lazy, I don't even want to figure out which rectangle it is. What I can do is I can move the origin, move my current mapping so that the origin goes to 3, 1. And the way I do that is I'm just going to literally move it. U comma v goes to 7u plus 2v plus 3, comma minus 5u. That's a plus, sorry. Plus 6v plus 1, right? I wanted 0, 0 to go to 3, 1. So if I stick in u equals 0, v equals 0, I'm going to get 0 plus 3. And I'm going to get 0 plus 1, so 3, 1. Okay, so this moves it so that I'm at the origin. All right, so now it literally looks like this guy going to that guy there. Okay. And you can check it. If I plug in 1, 0, I should get, what was that point up there? 10 minus 4. All right. Yeah, it looks like it's going to be okay. All right. Okay, so this creates my mapping. So for example, if I wanted to integrate, if I actually wanted to do integration, what is my Jacobian term? It's going to be determinant, again, dx du, dy du, dx dv, dy dv. All right. I always write it in this order. Technically, for the purposes of today, you could write dx du and then dy du on this next to it on the right hand side, and then dx dv down here, and then dy dv on that in the same corner. The determinant will just be the same, so it doesn't matter. All right. But I write it in this way because that's actually the proper way to think of this. Maybe I'll talk about that in a couple minutes. But let me actually finish this. So now I just calculate what each of these are, right? What is dx du? That's my x of uv. That's my y of uv. Right? So when we say dx dv, x is to be thought of as a function of u, right there. 7u plus 2v plus 3. Okay? So in this case, again, because things are linear, because we're working with a fairly simple mapping, these partial derivatives are super simple. All right. In general, they could be horribly complicated. They could depend on u and v. Just like when you do substitution, right? Your whatever you convert your dx to whatever du, that whatever in front of the du is often complicated. Okay. All right. Dx du looks like it's just going to be 7. Dx dv is just going to be minus 5. Dy du is just going to be 2. And dy dv is just going to be 6. All right. So again, this particular example, everything turns out fairly simple. 42 minus 10 equals 32. All right. So if I wanted to integrate, let's say integral over my parallelogram region of, let me actually do a function here. So xy squared, okay, dx, dy dx, let's say, or let me just write dA, right? What would my final integral be in terms of u and v? Well, it's going to be 0 to 1, u equals 0 to 1, v equals 0 to 1, right? We've already established that. Well, we constructed our mapping to do exactly this, right? Du dv, right? And then we have the kind of correction factor, which is 32, all right? And then we have to convert the x into y, right? What is x? X is, we just follow the instruction. X is 7u plus 2v plus 3, right? 7u plus 2v plus 3. And then the y was minus 5u plus 6v squared, right? And then now everything is in terms of uv, and we just do this integral just as a regular integral from second semester calculus, all right? Okay, equals, let's just say easy. Easy in that we already know how to do it, all right? Okay, so this is essentially our main, the main application for us for this kind of substitution or this extension of substitution to multivariables. So you'll notice one actually big difference with how we use substitution or change of coordinates in multivariables versus single variable. So in single variable, oftentimes your goal of substitution is to make it so that your integration, the function that you integrate, is easier, right? So for example, if you had integral in one variable calculus, x sine x squared dx, right? 0 to pi or whatever. What you do is you use substitution so that your integral in here doesn't look as nasty, right? U equals x squared, du equals 2x dx. And what that does is it transforms the integral into just sine of u du, right? 1/2. Okay, so that your integral becomes easier. That was how we used substitution in one variable calculus. And it worked really well because we didn't actually have to care about the limits of integration because they were simple, right? X equals 0 corresponds to u equals 0. X equals pi corresponds to u equals pi squared. No problem. All right. So the main goal in one variable calculus was to make the integral, the function, easier. But you'll see for us in this section, our main goal in terms of kind of this version of substitution is to actually make the region simpler. All right. So you can see in this problem, we made a horrible parallelogram region into a nice rectangular region. Okay. So they are actually, while they are literally doing the same thing, the same idea, the way we use change of coordinates in multivariables is different from the way we use substitution in single variable calculus. All right. Now, of course, you can do the same ideas in single variable calculus where you see a kind of a nasty expression as the thing you want to integrate. And so you do a change of coordinates to hopefully make that expression easier. But it's not as common because, again, your limits of integration are not as simple as in one variable calculus, where it's just a number to a number, right? So things are a bit complex. Okay, so just keep that in mind. We're using substitution in a slightly different way to make regions simpler instead of in a way to make the function simpler. Okay, so far we've been only looking at fairly simple examples, but let's say you want to integrate something like xy. You want to integrate between here, e to the x, and let's say here. Again, this is going to be fairly simple, but at least more complicated than our previous example. So let's say we want to integrate this between y equals 10 and y equals 20. So we want to integrate over this region here, right? And maybe this is kind of unpleasant perhaps because, right, e to the x and e to the x plus 3. Okay. So perhaps for whatever reason you don't like that, you would rather integrate over a rectangular region. How would you do that? Literally the same idea. So uv, you want to discover a mapping, x of u comma v, comma y of u comma v, right? Where the rectangle goes to this horrible looking region up here. Okay. How would you do that? Well, what you would notice is that this bottom portion of the region looks like e to the x, and this top portion is just e to the x, but just shifted upwards by 3 steps. All right. So if I do something like this, u comma v goes to e to the u comma, and it looks like here my horizontal part is just, these guys are just straight, right? So I'm just going to leave v as y, comma v, all right? Then what's going to happen is u comma 0 is going to go to e to the u comma 0. Oops, I shouldn't have done this all. Let me fix this, sorry. I shouldn't have done this all at once. Let me start again. U comma 0 goes to, I want u comma 0 to go to this guy right there, right? Or something like that, to exponentials, right? Exponentials, exponentials, all right? So I need this to go to u comma e to the u, all right? And notice, of course, this is what you would have used as a parameterization of e to the x. Okay, same idea actually, right? We're in a way parameterizing. This segment parameterizes kind of these kinds of segments, okay? And 0 comma v goes to, as we said, we just want this guy to go to this line here, right? Because if this guy just goes straight, then each of these straight guys is just going to go to a straight guy here. Okay, so 0 comma v. So our construction is or can be something like this, right? And so uv, goes to u comma e to the u plus v, right? That'll be a nice nice conversion, right? And we can check this. Let's see. When v is 0, u comma 0 goes to u comma e to the u, all right? So that's going to be this first curve right here, okay? When v is a constant, let's say over here, let's say v is 3, right? Then u comma 3 is going to go to u comma e to the u plus 3, all right? So it's going to be our previous guy shifted up 3 steps, and it's going to be this guy up here, okay? Let's see, when u is constant, when u is 10, for example, when u is 10, right? So here we're trying to integrate from 10 to 20, right? When u is equal to 10, right? U comma, sorry, let me write like this. 10 comma v goes to 10 comma e to the 10 plus v, right? What is that on the right-hand side? That's the vertical line right here, all right? It's been shifted a little bit, right? E to the 10 plus v, but e to the 10 is just a constant, right? So this means I'm integrating from, let me draw it down here. I already decided I want to integrate the, uv. I want to integrate from v equals 0 to v equals 3, right? And I want to go from u equals 10 to u equals 20. Okay, because 20 comma v is going to go to 20 comma e to the 20 plus v, right? Again, this guy here looks kind of unpleasant, but the important fact is that the thing on the right-hand side here describes a vertical line at 20, right? And above here, the important fact is that this right-hand side describes a vertical line at 10, okay? So what I'm trying to do is I'm trying to figure out what thing on the left-hand side of my equation corresponds to that segment right there. What thing corresponds to that segment right there? Okay. And so it's going to be these two guys over here. Okay. So ultimately my integral is going to be a double integral du dv, and then I'm going to have the kind of correction factor, whatever function I'm integrating. And again, the kind of reason we're doing all this is because we're doing u equals constant, right? 10 to 20. And v equals constant 0 to 3. All right. Okay, what is the correction factor? It's going to be determinant of, well, what's our function? X of uv comma y of uv, right, was equal to, and we're just going to copy it down from up here, right, u comma e to the u plus v, like that, right? So the upper left here is d, so dx, so that's this guy here, dx du, right? Dx dy du is going to be e to the u. Dx dv is 0. Dy dv is 1. All right? So this is just going to be 1. Okay? So our correction factor in this particular example is just going to be a 1 right there. Okay. Let's do polar coordinates. So what are polar coordinates? It's actually literally this idea. We've already kind of talked about it, x, y, right? And again, I'm going to stick with u and v, right? Polar coordinates is where we take a grid here and we turn it into that there. Okay, and the formula for the mapping is, well, just from the formulas for polar coordinates, here r is going to be played by the u, and theta is going to be played by the v. All right. It's arbitrary. You could do it the other way around if you like. But if we do it that way, this way, with u playing the role of r, v playing the role of theta, then the mapping is going to be u v goes to u cosine v, comma u sine v. Okay, r cos theta, x is equal, essentially just think of it as x equals u cos theta, y equals u sine theta. All right. Okay, so what's the correction factor in this situation? It's going to be determinant of the derivative of the x term with respect to u, so cos v, the derivative of the y term with respect to u, that's sine v, the derivative of the x term with respect to v minus u cos v, sine v, and then derivative of the y term with respect to v, so it's going to be u cos v. That's going to be that minus that, right? So it's going to be u cos squared v minus u times sine squared v. So that's just going to be u, all right? And we already know, right, when we do the correction factor for polar coordinates, from dy dx into dr d theta, it's r dr d theta. That's that u right there, okay? Because u is playing the role of r. Okay, notice one thing about polar coordinates that we do have to be careful about. It's not one-to-one, right? We said it's very dangerous when you have mappings where maybe, for example, 2 points here goes to 1 point there, right? And that exactly happens here because, well, when theta, right, goes from, well, let's say theta equals 0 and theta equals 2 pi are the same point, right? And then we also have this issue where r equals 0, all the thetas are same point, our origin, right? So you do have to be careful when using polar coordinates. But if you only are integrating from 0 to 2 pi, right, you're not going to be by accident repeating some parts of your integral, all right? But you do have to be aware of this, right? So normally when we do polar integrals, if you think about it, R is, so this, let me write it like this. This is my u, which normally we think of as r here, v, which is our theta, right? We're integrating from r equals, for example, let's say integration over a sphere or a circle, right? We're integrating from r equals 0 to, let's say, circle of radius 3, yeah. If we're integrating over the entire circle, right, on this side, the x and y side, we're integrating over circle. On the polar coordinate side, we're integrating over a rectangle like this, okay? So if we integrated over something bigger, like here, then we're going to be in trouble because here, this point here is repeating with that point there, okay? So you definitely don't want to be doing that. And same thing on the other side, kind of the second quadrant here, third quadrant, fourth quadrant, things are repeating, and so it's really dangerous, okay? So be very aware of this. Okay, in any case, this is another kind of way we can derive the r d theta. Okay. All right, finally, let's go to 3D. All right, so space. So in space, we would be integrating x, y, z. Right, now we want to convert it to something else, right? U, v, w, for example. Okay, and again, it's literally the same idea. We're integrating perhaps over some horrible looking region on this XYZ, in the XYZ coordinate system, right? In the XYZ space. But, maybe we can do a transformation or a mapping that allows us to integrate over something nicer, just a rectangle. Okay. So literally the same idea. We still have to do a compensation factor. And what is that going to be? Well, it's going to be determinant. And now it's going to be determinant of a 3x3 matrix. If my mapping is, I guess I should write out, if my mapping here is x of u, v, w, right, comma, y of u, v, w, z of u, v, w, right, then my kind of correction factor, my Jacobian, is going to be dx du, dy du, dz du, dx dv, dy dv, dz dv, and then dx dw, dy dw, dz dw. All right. So one way to remember this is you're going to all u's here, right? And you're differentiating x, y, z. All right. All v's here, differentiating x, y, z. All w's here, differentiating x, y, z. Okay. All right. So this guy here is going to be your correction factor. Okay. Actually, I should be actually a little more careful. Absolute value of this, right? Because this is supposed to represent in this case a volume, right? So of course it shouldn't be, because it's the volume of kind of the base, right? So it should be a positive thing. So absolute, if for whatever reason this determinant is negative, you absolute value it. Same with the two variable case. All right. Okay. So in terms of computations, it's very straightforward, right? You just calculate these guys and you do the determinant. How do you do the determinant? Well, just like what we talked about in when we talked about cross products, right? You do the crossing out, this cross that out, oops, and then this cross that out, this cross that out. Okay, I'll do one example in just a second. But if you've done linear algebra, then you're perfectly okay with this, hopefully. Okay, or done any sort of linear algebra. Okay, so of course one question is, why is this the correction factor? It's literally the same reason. If you think about linear approximation, then your linear approximation mapping, which is a linear approximation of your original mapping, is going to take rectangular boxes to kind of parallelogram boxes, right? What is the volume of that parallelogram box with respect to the volume of your original box? It's determined by this determinant right there. All right. How do you actually prove that? One way you can do it is from induction. You know it works in the 2D case, which we just talked about, and then you can expand on that to get the 3D case. And you can expand on that to get the 4D case, and expand on that to get the 5D case, and so on. All right. I'm not going to go through that, but it can be done that way. All right. Let's do an example just of this. All right. So one place where we've already seen this exact idea is spherical coordinates, right? In spherical coordinates, we use rho, phi, and theta. Okay, and we maybe we started out with x, y, z. We didn't like that. We wanted to convert to rho, v, theta. Right. So that's exactly the setting we have here. Right. Maybe rho would play the role of u. Phi would be like our v. Theta would be like our w. Okay. All right. I'm going to do this natively in rho v theta instead of u v w, just so we can see at least one example where I use kind of different letters. You definitely don't want to get stuck always thinking of the same, having to use the same letters. So in this situation, you would have your mapping would be rho phi theta, comma phi, comma theta, goes to rho, and then this is just a conversion from x equals what in terms of rho phi theta, y equals what in terms of rho phi theta, and z equals what in terms of rho phi theta. So this is sine phi cosine theta, comma, rho sine phi sine theta, comma, and then rho cos phi. All right, this is just our conversion from xyz to spherical coordinates. And so my conversion factor is going to be determinant of, let's see. So the first one is going to be the derivative of each of these. The first column is derivative of each of these with respect to rho. Sine phi, cos theta. Probably a good idea actually to just pause right now and do it yourself and see if we get the same answers. It's probably more helpful for you. But let me do it as well, just in case you run into trouble. So this is sine theta, This is cosine of phi, right? The next column is all three of these guys differentiated with respect to the second variable, which is phi. So it's going to be rho cos phi cos theta, rho cos phi sine theta, rho sine phi with a minus sign. Okay, and the last one is all three of these entries, x, y, and z entries, differentiated by theta. So rho sine phi sine theta with a minus sign, rho sine phi cos theta, and then 0. All right. Okay, so let's actually do the determinant. If especially if you aren't that comfortable with the determinant, you cross out the first row, first column. Sine phi cos theta is the thing that's completely crossed out. So sine phi cos theta times the determinant of what's not crossed out. So that would be that times that minus that times that, right? The two variable 2x2 determinant. Okay, luckily for us, that 0 helps us out a lot. This is just going to be minus rho squared sine squared phi cos theta. Okay, next we cross out. So we stay with the first row and we cross out the second column. The thing that's fully crossed out is the rho cos theta sine, cos phi cos theta. So this is rho cos phi cos theta times, and then the determinant of what's left, right? So what's left is this matrix, this entry, that entry, that entry, and that entry. So we have this times that minus that times that. Okay, again, we have a 0 there. So this is actually just going to be rho cos phi sine phi cos theta. Okay, and finally, we still have the first row crossed out. We cross out the third row now, third column, and we end up with a matrix, and we take its determinant, that times that, minus that times that. Okay, fairly tedious, but at least the nice thing is it's very algorithmic. I forgot the minus sign in front because, as we said, plus minus plus. Okay, so minus rho sine phi sine theta times sine phi squared minus rho sine theta, and then minus rho cos squared phi sine theta. Okay. And then we just simplify. And it looks absolutely terrible, but there's a lot of sine squares, cosine squares that will clean themselves up. So for example, let's see. The first one is actually, let me just actually multiply them out. Let's see. Actually, I think this was a plus. This was a plus because it was that times that minus that times that. So I have minus and minus, so that's a plus. Okay. Rho squared sine cube phi cosine squared theta, right? Next one's going to be, did I screw up the sign again? Let me take a quick look up here. Yep, I did. That times that minus that times that, right? So I should have had a minus sign here. I have minus, minus, they cancel. So I get rho squared cos squared phi sine phi cos squared theta. And then lastly, I'm going to get plus rho squared sine cube phi sine squared theta plus rho squared sine phi cos squared phi sine squared theta. Okay. Let's see. This term and this term go together because it's the same coefficient cosine squared, same coefficient sine squared. So those two just become rho squared sine cube phi. And then the other two, let's see, we've got this guy here times cos squared, and then the same thing here times sine squared. And so they add up to be just rho squared sine phi cos squared phi. All right. Okay. And then here we have sine phi times sine squared phi. And then here we have sine phi and then cos squared phi, right? So this is actually equal to rho squared let me actually write what I just said. So this is sine squared phi times sine phi, or let me write it as sine phi times sine squared phi. So this sine squared and that cosine squared go together. The two coefficients are the same. So we just end up with rho squared sine phi, right? Which is what we saw was the conversion for spherical coordinates. Okay, so working in three variables is literally the same idea. If you need to if you're integrating over a parallelogram region and you want to convert it to a rectangular region, you can do kind of the same idea with the linear mappings. Having trouble drawing a parallelogram region. Create a linear mapping as well, where you map a box to a parallelogram. All right. There's not going to be as many problems having to do with that, but for 3D, the really good example is polar coordinates, right? The really good example of this whole concept. Okay, and again, in terms of polar coordinates, if you were to draw a picture, right, if you are integrating x, y, z over a sphere, right, inside of a sphere, or a ball, a solid sphere, that would just be integrating over a rectangular box in the spherical coordinates, right? Rho would go from 0 to your radius, phi goes from 0 to pi, and then theta goes from 0 to 2 pi, right? So if I call this rho phi theta, for example, this height here would be 2 pi, that would be pi, and this would be whatever radius your sphere is, okay? All right, so this is a nice application of mappings, of change of coordinates. It's not the most important thing. It's important that you're comfortable with it, but it's not the most important thing, because what we're really going to do in this class is we're going to extend this idea to allow us to integrate over a sphere. All right, so we want to integrate over a sphere. That sounds completely foreign to us at the moment. But what we're going to do is we're going to do a mapping from this guy here to the surface of the sphere, right? Just literally like we said, a map. And then any problem here, if we have a function that's defined on the sphere, for example, temperature at a location on the Earth, right? We can kind of convert that to a function on this map, right? And then we can work on this map. We can integrate on this map. We can do calculus on this map. And it's much easier than working natively on the sphere. Okay, so that's what we're really, really interested in. But this kind of change of coordinates idea to help us integrate kind of difficult regions is a legit enough application. All right, so the last thing I'm going to talk about is what's the deal with this Jacobian of this matrix, right? So if we had our mapping UV goes to, let me just do the two variable case, goes to x comma x of uv, y of uv, right? Then we looked at this guy, dx, du, dy, du, dx, dv, dy, dv, and our Jacobian was the determinant of this matrix. So why, we explained that, this is the area of a parallelogram. And in three variables, it's the area of a three-dimensional parallelogram, extension of a parallelogram. I don't know what to name it, parallelepiped or something. What's the correct way to actually think about this? Well, the correct way is in terms of linear algebra. So if you've done linear algebra, this guy here is a linear mapping, right? It's a linear mapping so here's the correct idea. It's a linear mapping that takes the tangent space. Let me say it like this. It takes vectors here in the UV plane to vectors here in the XY plane. All right. So if I fix a point, let's say 3, 1, let's say it goes to 4, 5 here. All right. So this matrix here, if I evaluate at 3, 1, at 3, 1, at 3, 1, at 3, 1, this is just going to be a matrix of numbers. right? Once I've plugged in 3 comma 1s. So it's going to be, for example, 2, 1, 4, 7, something like that. All right. What is that? Well, if I take a vector here in the UV plane, all right, any vector here, let's say the vector 5 comma 10, right? And then I apply this matrix to the 5 comma 10, I'm going to get a vector which lives on this side at 4 comma 5, with it at its tail is at 4 comma 5, and the vector itself, when I do this matrix multiplication, it's going to be 10, 20 here, 20, 70, 90 here, right? It's going to be a vector that looks perhaps something like that, right? This mapping, this linear mapping from 3 comma 1 from vectors at 3 comma 1 to vectors at 4 comma 5, that's an important quantity. All right. That essentially is a linear approximation of your entire mapping. This guy here, in a way, represents the linear approximation of your entire mapping. And so this guy here, when you take the determinant of this, that's why it actually, like, for example, if I go, let me do it like this. At this point, 3 comma 1, I do that, right? That maps to that guy there, right? That's literally what we talked about when we did the area of the parallelogram. That was doing this mapping from here. This guy goes to this guy there. This guy here goes to that guy there. And then you calculate the areas. That was how we did the conversion, right? And it all depends on actually this linear mapping right there. All right. So the correct way to think about derivatives. So actually we said in one variable calculus, the derivative is just a derivative. In multivariable calculus, where you have f of x comma y, the derivative is supposed to be thought of as a gradient. All right. This is a vector. So in multivariable calculus, where you're thinking of x of uv comma y of uv, the correct way to think of a derivative is no longer as a vector, but as a matrix, whose entries are dx, du, and so on. Okay. And that matrix, through all of these, f prime tells you about linear approximation, gradient f tells you about linear approximation, we did that, and then this matrix tells you about linear approximation. And so it's actually a super, super important way to work with mappings. And so that's why you see it in our Jacobian expression. All right, it's a little too advanced for us, perhaps, because I guess a lot of us probably haven't had linear algebra. But when you do take linear algebra, you can try to remember this and remember that the basis of all this stuff that we're going to be talking about is actually based upon linear algebra in a way, because derivatives are linearizations of functions.